I'll describe Diffie-Hellman first, and I'll use an analogy that you can find in Wikipedia and other places, which is mixing paint. So in this analogy, there is some public value that is yellow paint, and Alice and Bob each have their own secret value, which is Alice's very special blue and Bob's very special red. So we know that Alice has some sort of secret paint, but we don't know exactly the shade of blue. No one else can produce that shade of blue, and the same for Bob's red. So how does this help us? Well, one thing we can do with paint is mix them together. And if Alice takes the yellow paint that everybody knows about and mixes it with her super special blue, we get some sort of green out. Similarly, Bob can take that same yellow and mix it with his special red and get some sort of orange out. Now, Bob and Alice are not going to send anyone their red or blue paint, but they will send them mixtures of that paint with the yellow. So Bob is going to send the orange paint that he gets from mixing yellow and red to Alice, and Alice will send her green paint to Bob. In doing so, they're not leaking their special color because we're assuming that this is a kind of paint where you can't easily take the yellow back out to get back to exactly the right blue or red. I'm going to adjust my gray boxes here to show that since Alice is sending Bob the green paint over the network, everybody can see that. So that is now public knowledge. But Alice is going to keep her super special blue paint secret still. What can Alice and Bob do now that they have these orange and green paint? And again, we're assuming that you can't take the orange paint and remove the yellow to get back to the pink. But what they can do is take their own colors and mix them again with the one that they got from the other party. So Alice can take the orange paint, mix in her special blue, and get some sort of brown out. Bob can do the same thing with the green. He's going to mix his red into green and he'll get exactly the same brown. This brown is now the shared secret. No one else can make this brown because even though they can start with orange or green, they don't know the blue or the red to mix in. They could mix the orange and the green together, but then they don't get quite the right brown. They would get a yellowish brown, and they can't subtract out half of the yellow to get to the right brown. So this is Alice's and Bob's shared secret, and now they can communicate. The only problem with this analogy is that we can't ship paint over packets, and so what we're going to ship instead is numbers. The yellow paint that everybody knows about is going to correspond to two numbers that we'll call P and G. Now P needs to be a prime number, so I'm using 13 as an example here, but in a real system, P is going to be a big prime number, something on the order of 1,000 or 2,000 or 4,000 bits. G is going to be a small integer. I'm using 6 here, but actually G is usually just 2. It doesn't need to be big, unlike P. But it does need to be known. Everybody needs to know about P and G. Alice and Bob, their secret color corresponds to some secret random number that they've generated. They can pick any number they want as long as between 0 and P. So if P is a 1,000-digit number, then A, as a random number somewhere between 0 and 1,000 digits, is probably also 1,000 digits. So that's a very big space of numbers, even in binary digits, that Alice can be sure no one else will guess the same number that she guessed. The same for Bob. He's going to pick a B in that same constraint, 0 to P. The process of mixing paint actually corresponds to this formula here. So mixing this A equal 5 as the blue paint with the yellow paint with P equal 13 and G equal 6 is take G to the A power, the public G to the private A power, and then take the modulo of that with respect to P to get some capital A. So lowercase a is the secret, capital A is the public value that Alice is going to let other people see. Bob is going to do the same. He's going to take his random number B, take G to that power, mod P, and get a capital B to share. With our concrete numbers then, 6 to the 5th mod 13, that turns out to be 2, and 6 to the 4th mod 13, that turns out to be 9. So Alice and Bob ship each other these numbers capital A and capital B. So Alice knows 9 and Bob knows 2. To mix the orange and blue, we do the same thing as when we mix the yellow and blue. So we take A equal 5 and raise capital B to the 8th power mod P. If B is 9 and little a private a is 5, 9 to the 5th mod 13, that turns out to be 3. Meanwhile, Bob does the same sort of thing. He takes the given capital A, raises it to his private B equal 4 power, so 2 to the 4th mod 13, that is also 3. And so you see what's important here, that Bob and Alice arrived at that same number 3. with small numbers like this, small p, g, a, and b, someone else could maybe figure out those numbers. But if they were very big numbers, then no one else would be able to arrive at these threes that Alice and Bob can arrive at.